Let us see some important terms connected with the simple harmonic motion. In last video, we have discussed simple harmonic motion, the expression of simple harmonic motion, what is simple harmonic motion, when a particle will execute simple harmonic motion, etc. So in this video, we will discuss some important terms connected with the simple harmonic motion. The first term is called amplitude of simple harmonic motion. Amplitude means the maximum displacement of the particle, that is oscillating particle, on either side of its mean position is called its amplitude. That is, we have seen in simple harmonic motion, the particle executes to and fro motion about its mean position. That is, the particle goes to two extremes on either side of mean position. So what is the distance between the mean position and one of the extreme position? That maximum displacement of an oscillating particle is called its amplitude. Amplitude is denoted by letter A. That is, in the equation x equal to a into cos omega t plus phi, or x is equal to a sin omega t plus phi, the term A is actually known as amplitude of simple harmonic motion. Now let us see some examples of it. Here you have a loaded spring, and you can see the mean position of that mass. When the system is disturbed, the mass will start oscillating about or between A and minus A. And you can see that motion is symmetric about its mean position, and hence the maximum displacement on either side from its mean position is found to be A, and hence A is the amplitude of this oscillation. Now let us see a horizontal oscillation. A particle starts moving to and fro about its mean position, and here also you can see that it moves to two extreme points A and minus A, and hence the amplitude is A. The next term is time period of simple harmonic motion. So what is time period? The time taken by an oscillating particle to complete one oscillation is called its time period. Now the question is, what is one oscillation means? One oscillation means the particle initially at its mean position moves to one extreme end, comes back to its mean position, goes to other extreme end, and back to mean position. This is called an oscillation. Time period is denoted by the letter capital T. Now here you can see a particle. Now it is at its mean position. Now when the system is disturbed, the particle will start oscillating, or it starts executing simple harmonic motion. Now from here we will have a correct picture of one oscillation. You can see here the particle starts moving towards one of its extreme end A. Then it comes back to its mean position. Now due to inertia, it overshoots that position and goes to the other extreme position minus A, and again comes back to its mean position. This is what we call one oscillation means. Now you can see that when the particle completes one oscillation, the path traced by the particle is an S wave or an S curve. Now the total time taken for this motion is T by 4 plus, T by 4 plus, t by 4 plus t by 4, which is equal to t, and that measures the time period. Now, what is t by 4? It is the time taken by the particle to move from its mean position to one extreme end. The next t by 4 is the time taken by the particle to move from that extreme point to mean position. The third t by 4 means it's the time taken by the particle to move from its mean position to the other extreme end. And the last t by 4 is the time taken by the particle to move from the other extreme end to the mean position. So it completes one oscillation. The total time will be the sum of all these time, that is t by 4. So when we add t by 4s, we get capital T, which is the time period of simple harmonic motion. Now, the third term, it is frequency. Now, what is frequency of simple harmonic motion? It is the number of oscillations completed in 1 second. So, how many oscillations a particle completes in 1 second measures its frequency. Frequency is denoted by letter F. Now, let us do one example so that the term frequency will be more clear to you. Let us consider an example. The time for one oscillation is t is equal to half seconds. That is, the particle takes a time which is 1 by 2 seconds for completing one oscillation. So, how many oscillations will be there in 1 second? See, t is equal to half seconds means it is the time for one oscillation. Now the question is, how many oscillations will be there in 1 second? I know that most of you have the answer. Now let us see whether that answer is correct or wrong. Now I have divided that 1 seconds into two halves, half second each. Now in the problem, it is given that for one oscillation, it takes half second. That means to complete one S wave, it takes half seconds. So in next half second also, it will produce an oscillation or it produces one sine wave. So you can see in 1 second there are two oscillations. So the frequency of simple harmonic motion in this case is 2. Now you got a relationship between F and T. The relation is F is equal to 1 by T. So by knowing the time period, we can easily calculate the frequency. So frequency is actually the reciprocal of time period. The SI unit of frequency is second raised to minus 1 or hertz. Frequency is also measured in terms of cycles per second, revolutions per second, rotations per second, etc. The next term is angular frequency of simple harmonic motion. Angular frequency means 2 pi times the frequency. If f is the frequency, then 2 pi f is the angular frequency. Thus, we have angular frequency omega. Omega, we usually denote angular frequency by the term omega. So, omega is equal to 2 pi times f, where f is frequency. And we know that frequency is equal to 1 by t. So, substituting, we get 2 pi by t. So, the relationship between angular frequency, and time period is omega is equal to 2 pi f, which is equal to 2 pi by t. The SI unit of angular frequency is radian per second. Now, another important term that is called total phase. What is total phase? Total phase of the oscillating particle at any instant gives an idea about the state of the particle with regards to its position and direction of motion. That is, total phase determines the state of an oscillating object. The state of an oscillating particle means it tells you the position of that oscillating body and in which direction it is moving. The position of the body, you can understand the position of the body, where it is now and in which direction it is moving. That is the importance of total phase. Suppose a simple harmonic motion is represented by x equals a sine omega t plus phi 0. X is position at a particular instant. A is the amplitude, omega the angular frequency, t time, and phi 0 is called the initial phase. In this equation, omega t plus phi 0 is called the total phase of the simple harmonic motion. And here phi 0 is known as the initial phase. We will discuss phi 0 later. So phi 0 is known as the initial phase. Omega t plus phi 0 is called the total phase of an oscillating particle. Now the initial phase of a simple harmonic motion. It gives idea about the position of oscillating particle at t is equal to 0. So what is the phase of simple harmonic motion when t is equal to 0? If a particle is at its mean position at t is equal to 0, then we know that its position x will be equal to 0. So substituting this condition in the equation x is equal to a sine omega t plus phi 0, we get 0 is equal to a into sine omega into 0 plus phi 0. And this equation holds true only when phi 0 is equal to 0. So in this case, when the particle is at its mean position, when we start the experiment, that is at t is equal to 0, then we can say that the initial phase of the particle is equal to 0. If particle is at its right extreme end at t is equal to 0, then we have x is equal to plus a. If it is at right extreme end, the position of the particle at a time t is equal to 0 will be capital A. So substituting in the equation x is equal to a into sine omega t plus phi 0, we get a equals, x becomes a, so a equals a into sine into omega into t is 0, so omega into 0 plus phi 0. And this equation will hold true only when phi 0 is equal to pi by 2. So at the start of the experiment, that is at t is equal to 0, if the particle is at its one of its extreme end, that is right side, then we have initial phase phi 0 is equal to pi by 2. Now let us see how position varies with time for a simple harmonic motion. That is, when the particles start executing simple harmonic motion, how the position of the particle changes with respect to time. Or if you plot the positions for different times, how it looks like. Now the equation of simple harmonic motion is x is equal to a sine omega t, and we are going to plot this. You can see that the shape of the graph will be an S wave. As it moves, the position changes, and if we plot all those points and connect all those points using smooth curve, it will be an S wave. So that plot of displacement with time is an S curve. Now, a plot of displacement as a function of time for two oscillating particles with different amplitudes and having same phase will be, you can see there, the amplitudes of the oscillations are different, but phase difference between the two waves is 0. Now we'll plot for equation x is equal to a sine omega t plus phi for two oscillating particles, and somehow we got a graph like this. Then from this graph, it is clear that the first wave, that is indicated by the blue line, at t is equal to 0, x is found to be 0. That means the phase difference is 0. The initial phase is 0. Whereas for the second wave, you can see that the initial phase is minus pi by 2. So these two variation will have a phase difference of minus pi by 2. That is, if the first variation, if it is represented as x is equal to a sine omega t, then the second variation, the second curve will have an equation x is equal to a sine omega t minus pi by 2. And these two variations has same amplitude. So in this way, you can plot different patterns with different amplitudes, with different phases.